Good morning, students. Welcome back to the session 2 of Unit 3, in which we are going to discuss about the mechanism of free radical polymerization, addition polymerization reactions. To sum up the last class portions, the preview of the last class portion is we discussed the differentiation between the different types of polymerization processes, particularly addition, condensation polymerization along with copolymerization reactions. Addition polymerization reaction is nothing but monomers having multiple bonds undergo this type of polymerization process, and we have the monomer and the polymer. The polymer is the integral multiple of the molecular weight of the monomer. Whereas in condensation polymerization, monomers having same or different functional groups will undergo condensation polymerization reaction, and we discussed examples for both addition and condensation polymerization reaction. Along with it, we saw about copolymerization reactions also. In this class, we are going to discuss about the addition polymerization mechanisms. So, the general objective of today's class is to understand and derive the steps involved in free radical addition polymerization process. To reach this general objectives, we are going to understand the mechanism of free radical polymerization, and with examples, we are going to discuss addition polymerization reactions having LDPE, Teflon and polyacrylonitrile. Now, the general reaction for addition polymerization can be given something like this. Let us take a monomer C double bond C, which is a olefin. You can see a monomer having a double bond. So, this is a monomer. We take a monomer. What happens in addition polymerization is you can take an initiating species such as Z star, which we call it as an initiating species, and this Z star, it attacks the carbon. The product formed will be where this may be a radical, cation or an anion. Further, there will be addition of another monomer, CH2 double bond CHR. I am writing it like this, which is again the monomer. Addition of another monomer will result in a propagating chain like this. See, we have this monomer RH, the first monomer from here, and again HH, single bond RH, and you have a species like this. If this monomer unit repeats n times, then what happens is you get a polymer. N times, you can write it as n times or n plus 1 time. Can also write it as I am giving it a 1. I am adding the same monomer, so n plus 1 time. So, this is your polymer that is formed. The general reaction can be for addition polymerization. You can give a general reaction like this, where you have a monomer, there is an initiating species that is added to it, and then this initiating species, it forms a radical center, a cationic center or an anionic center. Further addition of monomer will take place, formation of a propagating species like this, and a polymer will be formed ultimately in the end. So, this is how an addition polymerization reaction proceeds. Generally, addition polymerization reactions, it takes place in alkenes or substituted alkenes in alkenes or substituted alkenes addition polymerization reaction, and here what happens is the pi bond of the monomer will be converted to the sigma bond of the polymer. The pi bond of the monomer here, it will be converted to the sigma bond of the polymer. So, this is what takes place in an addition polymerization, and most of the addition polymerization, it is found to be exothermic in nature, where the energy released is between 8 to 20 kilocalories per mole. 8 to 20 kilocalories of mole is released, energy is released during addition polymerization processes. There are 4 types of addition polymerization. The first type is radical polymerization. The mechanism, radical polymerization, where the initiator will be a radical species and the propagating site will be a carbon radical. Second is cationic polymerization, where the initiator will be a acid and the propagating site, it will be a carbocation. Third is anionic polymerization, where the initiator is a nucleophile and the propagating site, it is a carbanion. Finally, we have coordination polymerization. In a coordination polymerization, the initiator will be a metal complex and the propagating site, it will be a terminal catalytic complex. So, these are the 4 types of addition polymerization. As I have told you, addition polymerization takes place where the monomer is having a multiple bonds. It may be a double bond or a triple bond, and the mechanism of addition polymerization, it is found to take place in via 4 different formations. The first one is radical polymerization, cationic polymerization, anionic polymerization, and coordination or Ziegler-Natta polymerization. In a radical polymerization, the initiator will always be a radical and a radical generating species. Radical or a radical generating species is taken as the catalyst to start the reaction, and the propagating site here, it will be a carbon radical. And secondly, we have the cationic polymerization, where the initiator is an acid and the propagating site is a carbocation. Third, we have anionic polymerization, where the initiator is a nucleophile and the propagating site is a carbanion. And coordination polymerization, otherwise known as Ziegler-Natta polymerization, which we are going to see in the forthcoming lesson plans. Ziegler-Natta polymerization, initiator will be a metal complex and the propagating site will be a terminal catalytic complex. Now, we are going to discuss about how this free radical mechanism operates. What are the steps that is involved in a free radical mechanism? Free radical mechanism. This proceeds via 3 steps. The first step is called as initiation. Second is propagation. And the third one is termination. Let us see with examples how these 3 takes place. First step is initiation. Initiation in a free radical polymerization takes place again in two steps. Step 1 is formation of initiating species. Formation of initiating species is the first step in the free radical polymerization. Let us take an example for polymerization of this CH2 double bond CHX. This is the monomer. N molecules of this monomer will polymerize to form the polymer CH2 single bond CH N times X. So, this is the polymer that is formed. We can write, we have already seen this example in the last classes as well as in the first session of here. So, step 1 is the formation of the initiating species, and here this initiating species may be of different. One is benzoyl peroxide may be used, or we can use tertiary butyl peroxide, acetyl peroxide, etc. All these may be used as the initiating species for this free radical polymerization reaction. So, if you have a monomer like this, you are going to add initiating species such as benzoyl, tertiary butyl or acetyl peroxide to this. Before adding to the monomer, we have this type of initiating species. So, what happens is, let us take an example of benzoyl peroxide. Benzoyl peroxide is nothing but C6H5CO, again OC, the same molecule. OOC C6H5. So, this is nothing but benzoyl peroxide. So, what happens is, this benzoyl peroxide on heating, you have two electrons here, one electron will shift over here and the other electron will shift over here, forming two molecules of C6H5COO, a radical. A radical is formed. But this does not stop here. The subsequent reaction is formation of phenyl radical 2C6H5 plus CO2. So, carbon dioxide is released here and you have phenyl as the initiating species, phenyl radical as the initiating species. So, this is what happens with benzoyl peroxide. Assume you are taking tertiary butyl peroxide. What happens? Tertiary butyl peroxide is CH3 thrice CO, again OC CH3 thrice. So, you have two electrons here, one electron on heating, one electron shifts here and the other electron shifts here. So, what do we get? CH3 thrice CO dot is what you get, and you have two molecules of this. Again, the subsequent reaction here is, what happens? Two molecules of methyl radical. You form methyl radical plus acetone. Methyl radical and acetone. So, this is what is the radicals. The initiating species here is the methyl radical and phenyl radical. This is nothing but tertiary butyl peroxide. So, tertiary butyl peroxide on heating, it forms methyl radical, which is your initiating species. Next is, we will see another example for this, azobis isobutyronitrile. The formula for this is CH3, as it is an azo compound, it will be having a N double bond N. N double bond N is your azo group. This is your azo group. The formula is azo bis iso butyronitride. So this is nothing but azo bis iso butyronitride compound. And this azo bis butyronitride compound, C, again we have two molecules of this. So CH3, CH3. So this on heating, what happens is you get a molecule like this, CH3 single bond C, CN, CH3 dot. So two molecules, two radical plus nitrogen. So this is your initiating species here. So this is nothing but azo bis iso butyronitride. So azo bis iso butyronitride is another example for the formation of initiating for the initiating species. I'll explain it in a simple manner. So you have this azo group here, N double bond N is the azo group here, and you have, let us take this whole group as R. Okay, so you have an R here and another R here. So what happens? How do we get this radical? One of the electrons from this bond, it gets shifted towards the nitrogen, and again this electron will be getting shifted towards the nitrogen, and the another electron towards this R. Here again another electron towards this R. So you get a product 2 R dot plus nitrogen. Okay, so this is your step 1. In a free radical mechanism, it involves 3 steps. The first step is initiation, and in initiation we have formation of initiating species. For that you take the catalyst such as benzoyl peroxide, tertiary butyl peroxide or acetyl peroxides. Let us call these as initiators. We take the initiators. This is the step 1 of initiation. Then comes step 2 of initiation. So what happens in step 2? In step 2, the initiating species attack of initiating species on the monomer will take place. So this is what takes place in the second step. What happens? Let us take this initiator. So I am taking this as R dot as the radical, so that for writing it will be easy. So I am taking it as R dot. Let our R dot be the initiator. The initiator is in your initiating species or the initiating, let us take it as initiating. R dot is the initiating species, and this initiating species attacks your monomer. See here we have taken the example of this. Therefore, I am writing the monomer as CH2 double bond CH single bond X. So this is nothing but your monomer. So you take the initiating species and the monomer, and what happens is this one of the electron from here and one of the electron from here forms a sigma bond or single bond. So a bond is formed CH2, and again there will be no double bond. You have only one electron that is left, which goes over the carbon. Single bond CH X. So you have one electron that is left out on the carbon. So this is nothing but chain initiating species. So, by using a very small amount of initiators such as benzoyl peroxide, tertiary butyl peroxide, acetyl peroxide, or your isobutyronitrile, all these small amount of initiators, whole variety of monomers, different variety of monomers, this X may be your hydrogen, CN, Cl, any variety of the C6H5, CH3. So, all varieties of monomers can be polymerized by using this, and the chain grows, and stable radical, more or less stable radical like this will be formed, and since the carbon radicals are stabilized by substitution of many kinds, the preference for head to tail, you can see head to tail, the preference for head to tail is understandable in this nature, and the radicals, so mostly most of the monomers will undergo only free radical polymerization. So we have only seen the initiation step now. So initiation takes place in two steps. The first one is formation of initiating species, and the second one is attack of the initiating species on the monomer. Next is propagation. Propagation of free radical polymerization occurs in two steps. The first one is, let us take this chain initiating species, which is RCH2 single bond CHX dot. Okay. So this is your chain initiating species which we got from the previous step, that is step 2 of the initiation. This attacks the monomer. Initially first monomer was attacked in the initiation process, and now it attacks the second monomer CH2 double bond CHX is your monomer. So it attacks the monomer 2. What happens? One electron shifts here, another electron also shifts here, a sigma bond, the pi electron is converted to a sigma bond, and there is shift of the electron from here. So what happens? RCH2 single bond CHX, and again we have the bond that is formed by the electron donation. So CH2 single bond CHX and a radical center here. So this is propagating species 1. Okay, let us leave this. So this is propagating species 1. But during a reaction, what happens? You have n molecules of the monomer. So let us take this propagating species 1 CH2 CHX, we can leave this brackets of CH2 CHX. Okay, this is your propagating species 1 that was taken from the previous step. It attacks the monomer 3 and n molecules of the monomer, so on. CH2 double bond CHX. So what happens? Your product that is formed will be a growing polymer chain like this. Now I can write it like this: CH2 single bond CHX n times, as I am taking n molecules, n times, and the terminal position will be like this: CHX, a radical. So this is nothing but propagating species, and this is otherwise known as living polymer. A polymer that is not dead, and it was assumed in principle that this will form a growing polymer chain of very high molecular weight, but in nature what happens is termination occurs after some time. Third step is termination. Termination may occur via two processes. One is coupling and the other one is disproportionation. Coupling or combination or disproportionation. So what happens? You have a living polymer that is formed during the propagation step, and this living polymer, let us take it to the termination step. R, CH2, CHX, N times CH2, CHX. Okay. So, this is a polymer propagating species 1. Okay. Plus, not this one, this is different. Let us take it as 1. Okay. This is PS1. So, PS1 propagating species 1, and again a similar chain like this may be formed. I am writing this in the reverse. Same thing, CHX single bond, CH2 single bond, CHX, CH2, N times R. Okay. This is propagating species 2. What happens in a coupling is, just these two come together and form a bond. So, I am writing product like this, CHX, N times CH2 single bond CHX, and you can see a bond that is formed, CHX, CH2, CHX, CH2, N times R, where this is your newly formed bond. So, this will be your newly formed bond. Can see this. This is coupling, just coupling between the two polymer chains will take place. Second is disproportionation. In a disproportionation reaction, what happens is, you can see here there is direct movement. Instead, what happens is, one of the hydrogen from the monomer will be transferred to the other chain, like this. So, what happens? Your polymer formed will be of this type, R, CH2, CHX, N times CH, double bond CHX, because one hydrogen got transferred. Therefore, you can have, see, 1, 2, 3, 4, the valency of carbon is satisfied here. Again 1, 2, 3, 4. So, this is what you call as unsaturated polymer. You have a double bond unsaturated polymer, and the other polymer, this one PS2, will be formed as a saturated polymer. Okay, I am writing it again in the same form, CH, I am reversing it, R, CH2, CHX, N times CH2 single bond CH2X. So, this is a saturated polymer. So, you get both unsaturated and a saturated polymer during disproportionation reaction. What happens in a free radical addition polymerization? It takes place by 3 steps: initiation, propagation and termination. In initiation, the first step is you have to take an initiator, subject it to heating, and you must form an initiating species possessing free radical. And this initiating species, in the second step, what happens is it attacks the monomer to form the chain initiating species where the initiation process is completed. Then comes the propagation process. The chain initiating species that is formed, it will attack the second monomer, third monomer, fourth monomer and so on to form a propagating species, or otherwise we call it as a living polymer. And this living polymer will undergo termination after some time, and this termination may occur by coupling or by disproportionation. Coupling is direct bond formation between the two propagating species, whereas disproportionation is the formation of a saturated and an unsaturated polymer. We can write this as, this structure, it is equivalent to, this R will be removed later on. So, CH2 single bond CHX n times. So this is the most favored process. Coupling is the most favored process, and this structure it is equivalent to this N. So this is what a free radical addition polymerization process mechanism is. Now let us see some examples of this polymerization. Example 1 is formation of low density polyethylene, which I am giving it as LDPE, low density polyethylene, and this low density polyethylene CH2 double bond CH2, here you can see the X is replaced by means of a hydrogen atom. So this in the presence of traces of oxygen or peroxides, and between a temperature of 350 Kelvin to 570 Kelvin and a pressure of 1000 to 2000 atmosphere, it forms polymer. This is LDPE, low density polyethylene, and this is ethene or ethylene. So ethylene to LDPE is formed like that, and this occurs via free radical mechanism. And it will be having a slightly branched structure also. One polymer chain may be grafted onto the other polymer chain. Slightly branched structures are also available. Mostly it is linear and branched structures, and they are chemically inert. This LDPE, it is found to be chemically inert to most of the solvents, and they are tough but flexible in nature, and they are poor conductors of electricity, heat as well as electricity. If you see the uses of this, as this is poor conductor of heat and electricity, they are used in insulation of electricity carrying wires. Insulation of electricity carrying wires. So this is one main application. They are used in squeeze bottles, toys, and even flexible pipes. In all these, this is used. And second is example 2. It is nothing but formation of Teflon. N molecules of Teflon is tetrafluoroethene. Or tetrafluoroethylene, again in the presence of heat and high pressure like 1000 to 2000 atmosphere, it will form Teflon, polytetrafluoroethylene or Teflon. So this Teflon is formed like this, and they are chemically inert again. This is also chemically inert, and they are non-corrosive in nature. Decomposition, it takes place only above 300 degrees C. Therefore, it may be used in non-stick cookwares. We have Teflon coating, double coating, triple coating, and so on. Oil seal, gasket. In all these, Teflon is used. And next example that we have here is acrylonitrile. Formation of polyacrylonitrile. So acrylonitrile is CH2 double bond CH Cn. Instead of X, there is replacement of Cn. N molecules of this under heat and high pressure, we have CH2 single bond CHCn. n times, and this is mostly used as a substitution for wool in the case of Orlon fibers and so on. So these are some examples of addition polymerization monomers that is undergoing addition polymerization reactions and through free radical mechanism only. So these are some examples. As we saw the examples of formation of LDPE, Teflon as well as polyacrylonitrile. So I hope you can write the mechanism for all these from the general mechanism that we have written. So we can take any type of initiator based on the monomer that you are taking, and addition polymerization through free radical mechanism can be carried out in the laboratory scale also. So this completes your session 2. Let us move on to the session 3, where we will be discussing about the cationic, anionic and Ziegler-Natta polymerization reaction in the forthcoming classes. We have 4 types of addition polymerization reaction, which is free radical, anionic, cationic and Ziegler-Natta. So we saw the mechanism of free radical polymerization. Next class we are going to discuss about cationic polymerization. The next class anionic polymerization and the comparison between cationic anionic polymerization, followed by Ziegler-Natta polymerization with examples of polymers that we use in the day-to-day life. Thank you.